All right, so we have an ideal gas you can find in a piston cylinder, and it's going to be air. And we know that it is at 20 psi and 40 degrees Fahrenheit, and we know that the gas occupies 1 foot cubed. So this is state one. It will undergo two processes. The first process is that it will be heated at constant volume, and the pressure will double. Then it will be expanded at constant pressure until the volume is doubled. Okay, and we want to know the overall heat that's associated with both of these processes together. We're going to assume ideal gas when I'm giving you here the specific heat to use. Okay, so what is it that we want here? Well, first of all, let's see how many states we have, how many processes we have, and what is it that we want. So we have state number one. Okay, and we'll try to define everything that we have directly. Then we're going to get to state number two, and we get there by at constant volume heating, the pressure doubling. That's the first process. We're going to call this process process 1 to 2, 1, 2. Then we're going to go from state 2 to state 3 using process 2, 3, and we're going to get there. So let's see what we have. So we know V1 is equal to 1 foot cubed. Okay. We know the original pressure is 20 psia. Okay. And we know the original temperature, which is 40 degrees Fahrenheit, which is the same as 500 Rankine. Okay. Again, we're always going to be in absolute. Don't use Fahrenheit and Celsius. Okay, so to get from state 1 to state 2, we know that we added heat, and we know that the volume stayed the same. So we know that V1 and V2 are the same. Okay, so we know that. And the pressure doubled. So this is an absolute pressure, so it's okay to double it. So P2 here would be 40. And we don't know what the temperature is. Something happens to the temperature. We just don't know. Okay. And to get from state 2 to state 3, the pressure remains constant, but the volume doubles. So we know that V3 is 2 foot cubed. Okay. And we know P3, we know the pressure remained constant. So it's going to be 40 psi. And we don't know the temperature either. Okay, so that's sort of what we have at the moment. Okay, we know it's an ideal gas. So what we could do is basically get all these the two temperatures that we're missing using the ideal gas law. So we'll do that first. Okay, so the ideal gas law is PV is equal to nRT. Okay, where N is number of moles, right? And we know for state 1, we have the pressure, we have the volume, we have the temperature. R is just looking up at the table, so we can find N. Why is that important? Because N will be the same for all of them. It's a closed system. So let's use state 1 to find the moles, which will give us the mass also. So using PV equals nRT, for state 1, we know that N is going to be PV over RT. Okay, which R should we use? Well, the one that's got PSI in it and foot cubed in it and Rankine in it. So you go look at the table and you find that it's going to be R is equal to 10.73. Okay, so we know that the pressure is 20 psi. We know the volume is 1 foot cubed. Okay, we know that the temperature here is 500 Rankine. Okay, and the R, I want something that's got Rankine for Q PSI. So you will go and you find in that table that 10.73 was the bill. And it's got its PSI foot cubed divided by pound mole times degrees Rankine, which is great because this cancels the Rankine, this cancels the PSI, this cancels the foot cube. Then I have 1/1 mole. And so this whole thing is in moles. Makes sense. So you punch all of this into the calculator and you get that you have 0.003728 pound mole of air. Okay, and we're going to use this information to do other things. Okay, cool. So for state 2, so this is state 1, state 2, what I am missing here is my temperature. Okay, so from PV equals nRT, right? PV equals nRT. I can just bring the nR to the other side like that, and I get T. So that's what I'll do. So PV, once I get to T2, I have P to V2 over NR. Okay, I have the N. It's the same N as all of them. They're all the same N. So that's great. Use the same R as before because it's the same units. So I have 40 psi. What's it? 1 foot cubed. N is that ugly thing, 0.003728 pound mole times the R is 10.73. And it's the same unit, PSI, foot cube, pound mole, R. So the PSI will cancel that, the foot cube will cancel that, the pound mole will be canceled by this, and I get Rankine. So I just omitted the units the same as that. I get 1,000 Rankines. Okay. So here, state 2, I got that this is 1,000 Rankine. Okay. And to get to state 3, so state 3, I also need to find the temperature. State 3, it's going to be the same exact equation. P3V3 divided by NR. And in this case, what happens is just the only thing that happens is that this thing doubles, the volume doubles. The mole stays the same, the pressure stays the same, the R is the same. So this becomes 2,000. So the last temperature is 2,000 Rankine. Great. So that's about all I could get out of the ideal gas law. And now I have all 3 states outlined for me. Okay. So that's what I want to do. Usually when I have an ideal gas system, try to define all the states, try to find all the variables that you have. And then now, whatever it is that you can't use the ideal gas law, use the, use the first law of thermodynamics to find. So we know it's the first law, we know it's a closed system, we know there's no kinetic and potential energy. And so what we see is that we have 2 processes. So I can apply the first law here, and I can apply the first law here. So to go from delta U from 1, 2, I'll get Q12 minus W12. And to go from state 2 to state 3, I can apply the first law of closed systems for this transition. And I will go from 2, 3, and that's going to be Q23 minus work 2, 3. Okay, we are not discussing any other types of work. So we'll just assume the only thing that happens here is expansion work, expansion contraction. So let's look at this thing here. Okay, for an ideal gas, the delta U, right? I'm going to erase this. I'm going to show you delta U for an ideal gas, for any ideal gas, is going to be the integral of CV dt from T1 to T2 or whatever. This gives me the delta U. So same thing here. That's true. Okay. And to get here for delta U, this is going to be the integral of CV, okay, dt from T1, which is 500, to T2, which is 1,000. Okay, now this is assuming total CV, meaning not a specific heat, but heat capacity. Okay, so meaning capital C. If it's lowercase c, which you could easily do, it's not a big deal. You could do the same thing. This is going to, I'm sorry, it says delta U 1, 2 is equal to this. Oh, wait a minute. Delta U 1, 2 is equal to either N CV dt or M CV dt. Okay, it just depends on the units of CV. What CV do I have? What's in pound moles? So I don't want to do that. I'll use N. I have moles. So cool. So I'm going to use this, and it's going to go from T1 to T2. Okay. And N we already calculated. That's that 0.003728 thing in pound moles. And we have this in 5.31 for the CV. So that means that for this transition from state 1 to state 2, delta U 1, 2 is going to be 0.003728 pound moles. Okay, times, I took the N out of the integral. The integral for 500 to 1,000 of CV, which is 5.31 right there, 5.31 BTU per pound mole degrees, or dt. Okay, so what happens when I integrate this? This thing here that I'm just dotting around, it's a constant. So it can also come out of the integral. And so the integral dt is just delta t. So what this means is that it's this number times delta t. Okay, we could do that. So when you integrate this, it just, this thing comes out of the integral. BTU pound mole R. Okay, so that's the CV, and we get delta T, and delta T is 1,000 minus 500 degrees R. And look at the units, the R's cancel the R's, and pound moles cancels the pound moles. So I get that I actually get the delta U for the process from 1 to 2 is going to be 9.90 BTU. Okay, so that's my delta U for this process. Okay, so let me just erase this. I can go back to that equation. So for my process here, I know my delta U here. So this guy here is 9.90 BTU. That's that thing. Okay, and I'm looking for Q. I want the overall Q, meaning I want Q12 and I want Q23, and I'll add them up, and that's what I want. That's what I'm being asked for. Find Q and BTU for the processes. Okay, so I need this one, I need this one, I need to add them up. Okay, since the only requirement that the only assumption I have here is that the work is expansion work. Expansion work is integral of PdV. So this here, work 1, 2, is from V1 to V2. I gotta integrate P with the volumes. Okay, cool. V1 is 1, V2 is 1, this thing's 0. So that means this goes to 0. Cool. So now I'm going to put that on the side. I have Q12 is 9.90 BTU. Okay, so I got my process from 1 to 2. I got that down for this thing. Great. Now I got to do this one, find my Q23 and add it to this guy, and I'm done. All right. Delta U23, same nonsense as before, is going to be here the integral of this thing. This delta U thing is integral of NCV dt. CV and N are both constant because just 5.31. They can come out of the integral. So this thing is NCV delta T. Okay, and I know my moles is going to be 0.003728 pound mole times this 5.31 guy, BTU per pound mole. degrees R times delta T, which is in this case from T2 to T3, so 2000 to 1000 minus 1000 degrees R, and it will cancel all of that out. So that means when I punch it all in, I get that the delta U here is about 19.8. Okay, so just erase all this nonsense. And this delta U here is 19.8 BTU. Great. I need to find Q. That's what I want. I don't know what that is. And work 2(3). Okay. Work 2(3). That's the integral of P dV from V2 to V3. Okay, so what's happening between state 2 and state 3? It's isobaric, so that means that it's going to be constant pressure. Isobarically expanding, the pressure will come out of the integral because the P is a number, not changing in this process. So I can just say it's going to be P integral dV, which means that it's P delta V between 2 and 3. Okay, so that's fairly simple. So that means that my work 2(3) okay, is going to be, well, my pressure here is 40, doesn't change for us, it's 40 PSI. And my change in volume is from V3 to V2. V3 is 2, V2 is 1, so it's just 2 minus 1 foot cubed. Okay. And so that obviously just becomes 40 foot cubed PSI, which is not BTU. So it's 40 PSI foot cubed, which I mean, unit wise, this is an energy equivalent, but that's not a standard unit. So we're going to have to convert this thing to BTU. Luckily, in the question, I gave us what that is. So we know that 5.404 PSI foot cubed is equal to 1 BTU. That's nice. So we can just convert this to BTU. Okay. 5.404 PSI foot cubed and 1 BTU. So that means that my work for this process is 7.40 out BTU. Okay, so again, I'm going to erase all this nonsense. That just becomes work 2(3). So work 2(3) is 7.4. Okay, blah, 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 blah. So right here, this thing here becomes 7.4 BTU. And so I can find that my Q 2(3) is 27.2 BTU. Okay. And then I'm not asked for Q 2(3). I'm not asked for Q 1(2). I'm asked for the Q in general. So my Q for my entire system from both processes, that's going to be Q 1(2) plus Q 2(3). And so final answer is 37.1 BTU. That's the amount of heat that is being absorbed by both of these processes.